Hello, I'm Michael O'Connell, and in today's video we're going to examine a problem in which we have a combustion reaction that produces a flame, and the main assumption we're going to make is that the process is adiabatic. So let's take a look at our givens, and we are given that we're at steady state. We already know that we have an adiabatic process that's going to be producing our flame, but what we're tasked with is finding the temperature of that flame. And let's think about what all of this means in terms of our energy balance. So as you can see here, there are a couple changes in energy that I'm not going to worry about. The main two I would like to point out is the kinetic energy of the molecules going in and going out, or the reactants and the products. I'm not going to worry about that. I'm also not going to concern myself with the small change in height with our burner here. That could have some small amount of energy change as well. But once again, I have to emphasize that we are at steady state, which means the left-hand side of our energy balance is going to be equal to 0 because we're going to have no change in energy with respect to time in this problem. So what does that leave us with our energy balance? Also remembering that we have no heat loss to the surroundings as our flame is produced here because this process is adiabatic. Well, that's going to leave us with two things. It's going to leave us with internal energy and work. And you may recall an equation that we have for that, and what that is going to be the change in enthalpy is going to be equal to the internal energy plus the PV work. So that's super convenient for us. So what does this mean for us in this problem? I said our left-hand side is equal to 0. So what I can write here, or I'll just say it before I actually write it so you hopefully can understand the concept, is that the enthalpy of our fuel going in that reacts with our air. So the enthalpy of the fuel and the air going in has to be equal to the enthalpy of the products that come out of our combustion reaction. So what that would mean for us is that we would have some enthalpy going in per some mass is going to be equal to the enthalpy going out. Okay. And we know that enthalpy is usually expressed in some unit like joules per mole, right? And that is going to be important for us. This leads me right into the next part here, in which we are going to do a little stoichiometry to figure out the ratios that we have before us. And fortunately, that also leads me into some of the givens here that I've marked in blue that were given in our problem. So hopefully you can kind of see those. Some of them might be a little hard to see because my camera quality is just not great. We have our natural gas, which, as you would expect, is 95% methane, so mostly methane, 4% ethane, 1% propane. Those numbers will be much more important for us when we try to find the temperature of our flame when we use Python code. But we have our air, which we're just going to assume is just that mixture of nitrogen and oxygen, and that's going to be 79% nitrogen, 21% oxygen, and that will be important here when we do our reaction stoichiometry. So let's write out our reaction with methane, right? So we have a combustion reaction, which means we're going to be reacting with oxygen. And notice there, I just said we're just going to be reacting with oxygen because we're producing a flame. This is a combustion reaction. So the nitrogen is not going to react with anything. It's just along for the ride. And again, that's only important for us insofar as we're using air to supply that oxygen to react with the natural gas and produce our flame. So what we're going to do in this video is just see how hot that flame is going to be. So let's think about this here. We have our O2, right? And then our N2. Okay, so that's our reactants. And I'll put our products under here so you can just see it as good as possible. Okay, so what is our products here? Well, we're going to produce carbon dioxide and water. jumping ahead of myself, obviously nitrogen is also still going to be there. As I said, it's along for the ride. Okay, let's balance this. All right, one carbon atom on each side. We have 2 oxygens, 1, 2, 3, 3 oxygens on this side. So let's put a 2 there. So we have 4 oxygens. If we put a 2 in front of our water, we have 4 oxygens on each side. We have 2 nitrogens on each side, so those are balanced. And then we have 2 times 2 is 4, and 4 hydrogens on each side, so that is balanced as well. Okay, the other important thing to note here is how does our nitrogen relate to our oxygen? Because the way we have it right now is a bit confusing because it's not our right ratio with our mixture of air, right? Well, what we need to remember there is that this is going to be, the air is 79% nitrogen and 21% oxygen. We have this multiplied by 2 as well. That's a good thing to remember. So our ratio is going to be 79/21 times this, right, for our nitrogen. But again, we have 2, so we also have to multiply by 2 as well. So if we're going to write this out accurately, this is going to be 2 times the 79/21 and 2, and the same over there. Hopefully, yep, perfect. So that is visible. Okay, excellent. So that's just one example there of the reaction we're going to be looking at. And I think we can also do one with ethane, and that's going to be just the same thing, just a different gas here, right? So our balance might look a little bit different, but we're going to have some sort of ratio for nitrogen once again. That it's going to correspond, whatever coefficient is in front of our O2 is going to be in front of our N2. So that's going to be important to remember. Then we have once again our CO2, water, and our leftover nitrogen. And I'm going to make sure that this is visible because obviously that is going to be down here. Okay. And you might also notice, now that you're looking at this kind of bottom area of the screen, we have 20% excess air. And that's another thing that we'll talk about more because that's going to be important when we write our code to solve this. Okay, so we have ethane this time. Let's start with our carbon atoms. So we have 2 and 1, so let's put a 2 here. Then let's do our hydrogens. The only other hydrogens on our product side is going to be in our water, so we'll make this a 3. Okay, so that's going to solidify our oxygens there, right? 2 times 2, 3 times 1. So we have 7 oxygens on this side, we have 2 on that side. So I'm not going to do whole numbers here, let's just give up, make it a fraction. What did I say before? This has to be the same over here, because we already have our 79/21 ratio there. Okay. Perfect. So now those are balanced, and that is very, very important for us. The other thing, actually, before we dive into the coding and a little extra fun, there is something else I should mention, which is that we are assuming that we have ideal gases here, and that will be important for that extra fun that I just mentioned. So specifically, when we're talking about enthalpy, and I'm going to erase these so that this will be more visible. But when we're talking about enthalpy, enthalpy can be represented. So we have the change in enthalpy as, so enthalpy can be affected by the change in temperature at constant pressure. It can also be affected by, as you would guess, change in pressure as well. Now, for an ideal gas, and this would be at constant temperature, for an ideal gas, this, again, when we're thinking about that pressure, that the particles don't see each other in an ideal gas. So this is gone. Thank goodness. Don't have to worry about that. But this is relevant, and this is so common that this is often referred to as C subscript P for pressure. And what that is the specific heat at constant pressure. Okay? And again, all of this should start to be kind of making sense. Why we have an exothermic reaction, obviously, with the flame being produced, but we're saying that the enthalpy in with our reactants has to be equal to the enthalpy of the products if we assume no heat losses, and that is true. So what does this mean for us? Well, this is going to make perfect sense, because where is that going to manifest? Well, there's going to be some change in temperature here, and that we are going to use that the fact that the enthalpy of the reactants and products have to be the same. We're going to use that using, you might be able to guess, the root solver to figure out what that temperature is going to be for our flame. So what we're going to do here next is get on the computer, jump into Python, and code this out and get a temperature for our flame.
Now we're ready to get started. So what I have here is the import of that link from GitHub that had our CHE tools. We have used this before, and we're going to be using the exact same thing. We're taking from CHE tools, we have che.py that has our class props with those properties. Okay, and that's going to be important for us because we need properties of all the compounds that we have for our reactants and products. So I have those stored in this variable p here. So that will be important for us. Now, the next thing we need to talk about is the equation that I had written on the board, which is represented here with our change in enthalpy. What we need to take into account is the fact that our change in temperature is probably not going to be very small necessarily. And what that means is that this specific heat capacity at constant pressure is going to change with temperature. And you might be thinking, well, it's just CP, like what do you mean it's going to change with temperature? But remember what I had written on the board. This is what I had written on the board, right? Because this is what the specific heat capacity at constant pressure is. And you see, there's this change in temperature, okay? But if that change in temperature is big, then we're going to need an integration to account for that. We can't just assume that this is going to be constant. So that means that this equation here is going to need to be integrated on both sides. And we're able to do that because we have our dH over here and our dt over here. So that is going to work out quite well. If we integrate dH, that's literally just going to be the difference in enthalpies, right? So that's not complicated at all, fortunately. And then our bounds of integration on this side, obviously, we are integrating with respect to temperature because that's what's changing and that's what's going to affect our specific heat capacity at constant pressure. So this is where the properties become important for us in our code. So what I have here is methane, properties for methane, and we have this ideal gas heat capacity, joules per kilomoles Kelvin, and we have these 1, 2, 3, 4, 5, A, B, C, D, E, 5 coefficients here for equation 107 from ChemCAD, in which this data comes from. This is that equation that I've snipped here for us. So as I said, we're going to need to integrate. What are we going to use for that? Well, we're going to use Wolfram alpha. And so I'm going to try to make this obviously as simple as I can. So we can break up these three terms, and we have constants B and D on the outside here. If we integrate A with respect to temperature, we're going to get A times the temperature. That's not complicated at all. And then we have these messy things, right? C over T, sine hyperbolic of C over T, that sort of thing. So let's see what that gives us. Okay, so integral, and then let's put this into Wolfram alpha. So we know that our integral here on the right-hand side is going to be equal to our change in enthalpy. So what we can do is kind of create two functions that will play off of each other. And let's kind of take a look at how we might do that, right? So let's define a function, and we'll call this the integral Cp. And obviously, we're going to put in a temperature value for that. So what are we going to return? Well, what we're going to return is exactly what we already have. So that's what I'm going to put in there. So let's do that. The one comment I want to make here that you'll notice when I code this is that where are we getting these coefficients, right? Well, remember, we are getting these coefficients from our data, and that is going to differ based on what element we have, right? What compound, I should say. So if I do PHFIG, that is going to give us the standard heat of formation for all of these gases, right? Notice that oxygen and nitrogen there, in proper order, are 0, right? Because they're O2 and N2. They're already in their plenteous form at standard temperature, pressure, all that good stuff. Okay, so we do have to account for that, right? So let's write that function as I had before. So we're going to put in our temperature, and then we are going to return this. The only difference is that we need to snatch those coefficients. So we need to figure out what those are going to look like. And I'll be honest, I'm not exactly sure. I want to say it's going to be PCP. Oh, they already popped up for me. Yeah, there we go, right? We want IgA times T. That's our first term. And then I can put in the rest of these. Let's create our second function now that we've integrated the right-hand side. The left-hand side there was the difference in enthalpies, right? And that's exactly what we want here. We want to be able to find the enthalpy at a given temperature, okay? Now, we have to think about where we're starting from with these compounds. We're starting at the heat of formation, right? They're in their most plentiful form, so that's the enthalpy here that we're going to return, which is going to be the P dot HF and then Ig because we're dealing with ideal gases. Okay, perfect. So that's where we're starting from with our compounds here. I just want to remind you where we're getting these from. Okay, so we are accounting for all of those. And then now we can use this function that we have. Now, one of them we're already going to be computing. The other we're not going to compute just yet, right? So we're going to have this integral Cp T, right? Now, what is that T? That T is the temperature of our flame, okay? Because again, in the end, we're going to use that root solver to make the difference in the enthalpy 0, because the amount of enthalpy of our air and our fuel that's going in and reacting and combusting has to be equal to the enthalpy of our products, okay? So that is what we have, so we're just subtracting that from the enthalpy here, and this would be what? This is room temperature, 298 Kelvin. Awesome. Perfect. So now we have our enthalpies. What we need to do is remember that these are on a per mole basis, and there is something actually very important that I'm forgetting here that I'm glad I just remembered. So let me pull up methane again so that it's visible here. If it will pull up for me. Come on. There we go. Sorry about that. Okay, so we had our ideal gas, heat capacity. Aha. So we have joules per kmol. That's coming out. What I just showed you which I'm not going to waste your time trying to find it. But when I did the heat of formation for all our compounds, right? Sorry, I forgot the P dot. These are on a per mole basis, right? These are joules per mole. So that's a problem for us, right? We need these to match, okay? So specifically, that means that these terms here from this function are on the per k mole, and then this is per mole. So that's wrong. That's not going to work. How do we remedy that? Well, we are going to need to divide all of this, return over here, yeah, it's flashing red, by 1,000. Use the dot just for the decimal. Okay, perfect. So now that's accounted for, and we are ready to continue. Now we have a function that can compute the enthalpies for our compounds, which is going to be extremely useful for us. But the last thing we need to do, now that we have that function, is we need to balance our chemical equations that we had before. So I've typed the two that I wrote on the whiteboard earlier in this video, and we are going to talk about these a little bit because they are extremely important. Now, if you're thinking back to probably chemistry in high school, when you're balancing chemical equations, obviously the whole point is to conserve mass. You have to make sure that the number of atoms for, let's say, your carbon atom or whatever element it is on the left-hand side of the reactant side is equal to the number of atoms on the right-hand side or the product side. Okay. Now, everything would be quite simple for us except for the fact that our natural gas has 3 components. Now, it wouldn't really matter that the natural gas has 3 components if they didn't all react, but they do. All 3, the methane, ethane, and propane in our case, react with the oxygen in a combustion reaction to produce carbon dioxide and water. The nitrogen is just along for the ride, and that's why what I'm about to do for the natural gas, I don't need to do for air, because the nitrogen in our air is the same in ratio, proportion on both sides of these balanced chemical equations that I have on the screen. So that's not going to be a concern for me in this point that I'm making. The point I'm about to make here is that we cannot just say that the number of carbon atoms that we have on our left-hand side is 1, and the number of hydrogen atoms we have is 4. Now, why can't we say that? Well, we can't say that because we don't have just methane. We have 4% ethane and 1% propane as well. So what we're going to need to do is do a special matrix multiplication that I think is very neat that will actually give us the real amount of carbon atoms that we have. I shouldn't say real. It's really a relative amount of carbon atoms that we have and hydrogen atoms. Okay, we need to get the right ratio because, again, it's not just 1 and 4. It's not just methane reacting in there. And again, we don't have to do this with the air because the nitrogen appears in the same proportion on the product side as well. It's, as I said before in the beginning of this video, it is simply along for the ride. Okay, let's begin. So let's use numerical Python to make an array. And this will be very simple, right? Let's just start with what we were given in the problem. We were given that there is 95% methane, 4% ethane, and 1% propane. What do I have here before you? I have a 1/3 matrix. As I said, we're going to want to perform matrix multiplication so that we figure out the actual relative amounts of carbon atoms and hydrogen atoms that are on our left-hand side so that we can balance our chemical equations. And specifically, we're balancing it overall, okay? Because as I have in this document, I have 2 of those 3 chemical equations that we could have balanced. We could have done one for propane as well. You'll see why I don't need to do that, at least in this video. I can save time and not write that out because what we will use this for very soon, I only need these 2 equations to make my points there. So that will be good for us. So we're talking about the atom ratios. Okay, so I'm going to make another array. And as I said, we're going to be performing a matrix multiplication. Now, this array, obviously the inner dimensions need to match, okay? Which means this one needs to have 3 rows and then a certain number of columns. Now, how many columns would it have? Well, I would ask you what atoms are we dealing with? These are hydrocarbons. They just have their number of carbon atoms and the number of hydrogen atoms, and that's what we're after. So we can represent that for methane, which is going to be 1 carbon atom, 4 hydrogens, and then our second column is going to be our ethane, which is going to be 2 and 6. And then our final column is our propane, which is 3 and 8. Okay? And again, this all makes up 2 different... I'm having a very hard time describing this with the columns and rows. It's very, very easy to get mixed up because I'm not drawing this out on a whiteboard. So 3 by 2 matrix. So 1, 2, and 3. These are the rows, okay? So think of it like this, right? 1, 2, and 3. And then your columns, okay? So your first row, that is your number of carbon atoms, right? 1, 2, 3. And then your hydrogen atoms, 4, 6, 8, okay? Now, you might have been able to put those pieces together, okay? If we perform matrix multiplication with our percentages, right? The 95%, the 4%, the 1%, and we add them together, right? It's kind of like a weighted average, right? So what we can do is actually compute the relative number of carbon atoms that we have on that left-hand side and the relative number of hydrogen atoms. And as you might expect, so this is mostly methane. So what we get, it's going to be close to 1 and 4, right, when we do this matrix multiplication, okay? And we use the @ symbol for this, right? And I'm going to unpack this into the number of carbon atoms and the number of hydrogen atoms. I do have to make sure I do that in the right order. So we'll do NC, comma, NH. Okay, so we're unpacking this. And let's see what we get for this. Okay, got a check mark. That's a good start. So number of carbon atoms, 1.06. That's what I would expect, wouldn't you? Because most of this is methane. So we're going to be pretty close to 1 carbon atom, but we're going to be a little more than that. We're going to be a little higher than that. Why are we going to be higher than that? Well, ethane has 2 carbon atoms, and the propane, small amount, has 3 carbon atoms. So we're going to be we're going to have a little bit more than just the 1 carbon atom. But we're going to be close because, again, our natural gas is mostly propane. Similarly, for hydrogen, we're going to be pretty close to 4, but a little bit more. So we're at 4.12. Excellent. So this is very good for us. Now, what do we need to do next? The next thing we need to do is figure out the number of moles of our other components. And this is where I'm going to refer to the 2 balanced chemical equations that I did type out and the ones that I wrote on the board earlier. I'm going to use these 2 balanced equations to demonstrate this. And like I said, I'm only going to need 2 of them. I'm not going to need all 3. So we have methane here, CH4. Okay, so we have our number of carbon atoms. And as you can see with our amount of CO2, or the number of CO2 molecules we have here, it corresponds directly to the number of carbon atoms we have. We see here we have ethane, so there's 2 carbons, and then we have 2 CO2 molecules. So there you have it. So let's put that in here. So that means NCO2 for us is going to be equal to NC. Let's do water. Number of water molecules. Okay, so we have the number of water molecules here, and there's 2 of them, and then there's 4 hydrogen atoms. Then we have 6 hydrogen atoms and 3 water molecules. So 4 and 2, 6 and 3. So that means we are just going to take the number of hydrogen atoms we had and divide it by 2. Okay, next thing we'll do, let's do oxygen. Okay, and then we'll do nitrogen. And I want to do oxygen first because we have that 79/21 ratio of nitrogen to oxygen. So the nitrogen is going to relate to the amount of oxygen we have. Okay, so this is going to depend on the number of moles of hydrogen and carbon dioxide that are produced actually for us, which I am going to attempt to show you here. So we have 2 O2 molecules. We have 1 carbon dioxide molecule and 2 water molecules. Okay, so you might be thinking, well, it seems like this does correspond just directly to the amount of water molecules. And that'd be a good guess based on just one equation, but fortunately, this is why I made the second balanced chemical equation, because here we have 3.5 O2 molecules on this side. We have 2 carbon dioxide molecules, and then we have 3 water molecules. So there is a subtle pattern here, okay? Let's look at the second one, right? So I have my 2 CO2 molecules. If I divide 3 by 2, I get 1.5, okay? 2 plus 1.5 is 3.5, which is the amount of O2 molecules that I have. Let's see if that pattern works for this chemical reaction that's balanced here above. Once again, I have 1 CO2 molecule, and then plus half of the water molecules I have. So half of 2 is 1, so 1 plus 1 is 2. So that pattern works as well. Okay, so that means for the number of oxygen or O2 molecules that, or moles, moles of O2 molecules that we have, it's just going to be NCO2 that we have above plus NH2O. Whoops, didn't want that. Divided by 2. Okay, make sure I did that right. Excellent. Okay, now we have the number of nitrogen molecules, and that is simply going to be equal to 79 divided by 21 times NO2, and just to be safe, I'll put these in parentheses. Okay, what am I forgetting? So with our problem statement, we were given that there is excess air, okay, by 20%. So what that means, these are the exact molar ratios you would need for just the complete reaction, but we have excess air by 20%, so we're just going to be able to multiply the amount of oxygen by 1.2. But just so that in the future someone could adjust this, let's call this excess air, and this is going to be 20%, okay? Now, I can multiply this by that, right? Excess air plus 1. And then I don't have to worry about my nitrogen because the number of moles of nitrogen is already based on the number of moles of oxygen. Okay. Now we need to specify the number of moles that we have going in, right? Which needs to be balanced with the number of moles that we have going out. Okay? And for this, we are going to need to add 2 arrays together because we need to account in proper order the moles of all of our compounds, okay? I say proper order because we specified in our thing up here, the variable P, props, this class, we have our objects, which are our compounds, so we need these to be in proper order, right? Okay, so how do we add or combine arrays together? That's going to be NP concatenate. Oh, thank goodness. I love when that comes to my aid because I genuinely need it. Okay, so let's add some arrays together. So the first array that we're going to need is the, well, like I said, proper order. So we have our moles of natural gas in this array here. So Ng mole. And then, in fact, I think I need to put this in brackets. Okay. Comma. And then we're going to make another NumPy array. Okay, so what would this have? This will have it in proper order, right? 0.95, 0.04, 0.01, methane, ethane, and propane. So we're good there. Okay, what about our oxygen and nitrogen? Okay, what about those guys? Well, we can do that in proper order because we have those up here. So we have NO2, and then N2. Ooh, now what about our carbon dioxide and water? this, you got to be a little careful, right? So this is what's going in. So these are going to be 0 going in. Okay. Okay, excellent. So that's specified. Now, what about what's going out? What is that going to look like? Well, once again, we're going to make an array of this. Okay, let's think about this. I'm trying to be as careful as possible because it's very, very easy to get lost here. But what this is going to consist of simply is just our products, which are going to be the carbon dioxide and water. So let's think about that here. So we have the NCO2, right? And NH2O. And then what about everything that reacted to create that? How are we going to account for that? So we don't have to worry about the natural gas, right? Because that's reacting completely. But we are going to have excess air that we are going to have to be concerned about. So what are we going to have left? Well, as I said here, we're going to have zeros for our hydrocarbons, our natural gas. So I'll put those in there. Okay. Now what about our oxygen? We need to do this in proper order. Well, again, all we're going to have left is whatever excess there was, okay? So we can just specify that as NO2 times excess air, okay? So that's good. And then, again, nitrogen along for the ride. So it's just N2. No problem. No problem at all, right? Excellent. Let's see. Oh, we do have an issue here. Okay. Oh, yeah. So a couple of problems with this. This little bracket there, that should not be there. So we're making a new array that's combining two. So we have ng mole, and then we want our comma numpy array. So this array, and then I have that closed off. So I need a square bracket there as well. And then I have that closed with parentheses. Okay. Hopefully that should work. Nope. Something. Oh, geez. That is embarrassing. Really, really bad spelling on that. Okay. Excellent. Now we are ready to move forward and get the temperature of our flame. Now we're ready to use the root function to find the temperature of our flame. Now, we balanced our chemical equations. So what we need to do is use our function that finds the enthalpy of each compound. And we remember that those enthalpies are expressed in joules per mole. And that's why we balanced our chemical equations. So what we need to do is use our number of moles in and number of moles out and our function that computes the enthalpies at a certain temperature. We need to perform element-wise multiplication. Okay, and to do that, we need to do a dot product, and numerical Python has something that we can use for that. It's just np dot dot, and then we put the two arrays in that function. So that is what we're going to be able to use when we create this function that we're going to use the root solver on. So let me make sure. Yeah, so I have from SciPy the root function. All of that. Okay, I just wanted to make sure. And we should be all good to go and ready to move forward. So what is that going to look like for us? So we get to define some function. We'll call it temp. Okay, or temperature. And then we'll put in our vector. Okay, and then we have that t variable again. And then I'm just going to do vec and the first element. Because, again, our guess that we're going to specify is just the temperature. Okay. Now, what are we going to return? Well, we're going to return a difference. Now, what we need to return also needs to be an array when we're using the root solver. Okay. And we are going to have the dot product of our what's going out, right? Because, remember, I had the enthalpy of the products going out set equal to the enthalpy of the products going in, but per unit mass, right? And that is what we're doing the element-wise multiplication for. So what is that going to look like? Well, that will be How do you spell it? Enthalpy T, right? And then multiply that by an out. And then we're just going to subtract that from the same way. But the only difference here is we need to have this be our room temperature, 298, and then that would be what's going in, right? Okay, perfect. So that should work for us. Now, what we need next is our root function. We put in our temperature, so we put in the function. And then what we need here is a guess. And we'll put that in as a vector. Let's guess 2400 Kelvin for the temperature and just see what that gives us. And we do have an error. And let's see if we can maybe figure this out. Fortunately, I was able to find a remedy for the error that appeared before us. And all I had to do was run time all. And once it goes through, it actually does return the temperature. I just grabbed the X attribute and indexed that to 0, so to get it out of the array. So this returns the temperature of our flame, which is very hot, 2063.75 Kelvin. So I hope you enjoyed watching this video, and hopefully you were able to learn a lot from a different type of energy balance problem that we tackled in this situation. So thank you so much for watching.